This video is for an introduction to compounds that contain benzene rings. Okay, benzene ring is something that has 6 carbons like this in a hexagon shape. And each of this is bonded to another hydrogen. And if you look at a carbon, there's only 3 bonds there. So where's the 4th bond? You can imagine as if there's a double bond here, here, and here, but it's actually not like that because the electrons are delocalized. For HL, you would need to know that that would be the pi bonds. So it's delocalized here. So if you look at this picture down here, it's actually the p orbitals here. They actually overlap each other. That is why it forms a pi bond in the middle. So that completes the 4th bond. So 1, 2, 3, and 4 is in here. We call these compounds that contain this benzene ring aromatic compounds, and as opposed to aromatic, that's aliphatic. So aliphatic compounds, they are like the ones you've always learned, the straight chains or like maybe some branches. So those are aliphatic. But if they contain this benzene ring, then we call them aromatic compounds. This skeletal way is the most common way to represent our benzene ring. And it could have like a methyl or ethyl on it. And the general formula would be CnH2n minus 6. So for example, if we have a methyl benzene, so I can write it like this, a methyl, or perhaps like this, methyl. Or perhaps like how I draw it just now. So in this way, I showed every bond. So there are many ways to represent methylbenzene. So let's look at this general formula. So methylbenzene has 1, 2, 3, 4, 5, 6, 7 carbons. So C7, H. So there's 1, 2, 3, 4, 5 on the ring, and 3 more on the methyl itself. So that makes 8. So H8. So isn't that N? 2n, that's 14 minus 6, so we get 8 here. So this is the general formula for compounds that contain the benzene ring. Okay, let's look at this ring structure here and relate it to the alkene that we learned much earlier in the academic year. If you have 1, 2, 3 bonded pairs, it's going to be trigonal planar. So it means that this whole ring is flat. So it's planar, it's symmetrical, and it's non-polar because there's no one side that has more electrons than the other side. However, if you look at this picture down here, these are the p orbitals, and the p orbitals all overlap, all 6 of them. And so there are the delocalized electrons in there, which makes the pi electrons. That is this area here in the ring. And because of that, it's actually rich with electrons in the ring, although we say that it's non-polar. Okay, this ring system is actually stabilized by the delocalized pi electrons. Therefore, it's resistant to oxidation and addition reactions, although there are some exceptions that it can undergo addition, but it's not common. We'll not cover addition in this introduction video. So to preserve this system, where there's the delocalized pi electrons, it most of the time undergoes substitution where the ring system is still there. So if we look at this system, we often represent it this way. We'll call this the phenyl group. So that's C6H5 and CH3. So this is how we represent a methylbenzene in the condensed structural formula. For HL students, later on we'll cover reactions for benzene ring, and you'll find that most of the time electrophiles will attack the benzene ring because of the electron-rich area here.